Hello everybody, this video clip is the first video clip for chapter 6, which is about the differentiations of the function. Okay, so for this chapter we are going to learn how to define a derivative of a function, as well as some of the application that you haven't touched on your math 1 or math 2. However, some of the calculation, okay, you still need to remind yourself about all that calculation in your math 1 and math 2 as well. So the first thing that we would like to remind you is that throughout this chapter we are going to use the letter capital I, okay, to represent an interval on the real number. Okay, for example, that I can be closed interval AB. Okay, so the first talking about the definition of the derivative. Okay, so letter has the f, that is a function from I to a real number r, and one of the element in the I called the c. Okay, we are going to say that your f is said to be differentiable at c if the limit as your x goes to c of the quotient fx minus fc over x minus c exists. Okay, and in this case this limit is called a derivative of f at c, and it is denoted by f prime at c. Okay, so for example, if this one exists and it is equals to L, so it means that for any epsilon given, you can find the delta, okay, such that for all x within this interval I, okay, and your x, okay, away from c less than L, okay, your f of x minus f of c over x minus c subtracted by L less than epsilon. However, because this definition, okay, you are going to use the function value at c as well, so it means that your x and your c, okay, can be the same. So the implication or the condition on your x here can be only that your x and you see the distance among them less than, oh sorry, less than delta. Okay, less than delta, then the f of x minus f of c over x minus c minus L will less than epsilon. Okay, so this is the same old limit definition as we have for our chapter 5. Okay, so for example, the one that we usually have, okay, at the first place is that if your f is defined by f sub x equals to x to the power n, okay, then we know that the derivative of this function at the point c, okay, will be just kick down this n, okay, and then lower the power of your x by 1, and then you replace your x by c for any real number c. So let's see how this happened. Okay, so for we let your x is not c first, okay, and your c is any real number, then you can calculate this quotient, your fx minus fc over x minus c. Okay, so this one is simply x to the power n and c to the power n over x minus c. Okay, and you should know that on your top it is simply x minus c, okay, as a factor, and then this one will be x raised to the power n minus 1, x n minus 2 times c to the 1, x n minus 3, and then c square, and you add up to x to the power 1, c raised to the power n minus 2, and the last one will be your c raised to the power n minus 1, and it is still over x minus c. However, because right now you're talking about all the x that is not the c itself, so it means that this one is not going to be 0. So you can do the cancellation. Okay, so what you have left, it is all the factor okay, that you factor out, and each of them, I mean the first one that we got, it is x raised to the power n minus 1, okay, etc. to x, and then c n minus 2, c n minus 1, and all these terms, okay, because you are going to, I mean, you start from x raised to the power n minus 1 up to x to the power 1, and actually you have x raised to the power 0, okay, at the end. So it means that you got really n terms, right? Okay, you have n terms add together. So at the end, if you need to replace your x by c, okay, as your limit go close to the c right there, okay, so it's just simply the limit as your x goes to c of that expression, okay, the n terms expression, you add them up to x c raised to the power n minus 2 and c raised to the power n minus 1, okay, and because it is all polynomial, right, and if you can remember, the polynomial is continuous, so the limit will be the same as your function value, so you can just replace all the x by c, okay, and the power will be, I mean, all power, because for example this one, you have c raised to the power n minus 2 combined with c to the power 1, or c raised to the power n minus 3 combined with, I mean, multiply with c raised to the power 2, then all, I mean, each term becomes c raised to the power n minus 1, and you got n terms added, so it means that you have n c raised to the power n minus 1 as your derivative, okay, and this one will denoted by f prime at c, okay. And if you look at the definition of the derivative, which is depends on this quotient, okay, which is depends on this quotient, then you may see that this one on top, okay, it seems to be that if the limit of this quotient exists, okay, and you can get rid of the bottom, okay, if you can get rid of the bottom, it means that your f of x and your f of c should be the same, all right, under the limit, okay, and if under the limit your f of x and f of c are the same, then it means that your f is actually continuous at that particular point, okay. So that's the one of the most important theorem, or sometimes we call in immediate result that came from the definition, is that if your f, okay, from I to r is a function, okay, is differentiable at the point c, then your f is immediately continuous at that point, okay. However, the converse is not that true, okay, so the converse is not true in general. For example, the absolute value function f from r to r defined by f of x equals to absolute value of x. This one is of course continuous, but it is not differentiable at 0, okay. We are going to talk about this remark later on. Let us simply do the proof of this theorem first, okay, it's not that difficult. So we let your x be arbitrary in this set, in this interval I, okay, except the point C, all right. So we have this one, because as I told you that if your f of x and your f of c are equal under the limit, then we can conclude about the continuity, right? But actually this one, it is the same as the quotient of f of x minus f of c over x minus c, and then just simply multiply by another x minus c, right? Okay, and since the f prime as c exists, okay, because it is differentiable, then this limit, okay, one of the parentheses here, the limit of this quotient, okay, f of x minus f of c over x minus c exists. Okay, so what does this mean? You can just insert the limit, okay, both sides, just like that. It will be equals to the limit of this one, the quotient, and the limit of this polynomial, right? This one is simply a polynomial. Okay, and again, a polynomial is continuous always. So, and in particular, it continuous at c. So the limit of this polynomial will be the same as the function value. So this one you can just replace your x by c, and it becomes a what? It becomes a 0. This one, it exists as a real number. So any real number multiplied by 0, you got what? You got 0 as a result. Okay, so it means that the limit as your x goes to c of your f of x, okay, it is simply equals to f of c. Okay, so it means that your f is continuous at x equals to c. Okay, so now if you look at the remark, okay, for the remark, if your f is simply the absolute value of x, and you should know that the graph of this function look like a V shape like that, okay, that have this 45 degree with your x-axis, okay, and this one you got the like the angle over here, okay, and at this angle that will be something that make your derivative does not exist. Okay, so for the graph that has this kind of angle, okay, so in other words it's not smooth, okay, then your derivative will not exist over that point. Okay, so let's talk about the quotient that we are going to calculate for the derivative. So if your f is not 0, the quotient that we need to define, okay, to find the derivative at the point 0. Okay, so we are going to claim that the derivative at 0 does not exist. Okay, so this one, it is actually the absolute value of x minus 0 over x minus 0, which is simply this one. And do you remember this function? It is a signum of f of x, right? And from chapter 5, we know that this limit as your x goes to 0 of this function signum of x does not exist, right? So it means that your absolute value is not differentiable at this particular point. Okay, at this particular point. However, of course, the limit as your x goes to 0 of the absolute value is the same as the absolute value of the limit, and it is 0 itself, which is the absolute value of 0, right? Okay, they are the same at the first place. So it means that, let's say that this one is f at 0, and this one is the limit of your f of x. Okay, they are the same at the first place, so it means that the function is continuous at continuous at x equals to 0. Okay, so this one, the function is continuous, but it is not differentiable. However, if your function is differentiable, we can conclude immediately that your function is continuous at that point. Okay, and you may ask yourself, how about the derivative, okay, of this function where your point is not 0? Does it exist? And if it exists, then it equals to what number? Okay, so you may ask yourself this and to try to do it at home. All right. Okay, and next we are going to take a look at the derivative rule that you have learned in your math 1. For example, if you got constant, okay, but of course your f and your g must be differentiable first, okay, at the particular point c. If you got a constant multiplied by that function, okay, and then you find a derivative, it means that you just simplify a derivative of this function, okay, and at this point, and then later on multiply by this alpha. Okay, if you got two functions added together and find a derivative, it is the same as finding a derivative of the first one at that point, a derivative of the second one at that point, and then you add them up. However, to have the product, if you got f times g and then derivative, it is it means that you find derivative of the first multiply the second plus the first multiplied by the derivative of the second. Okay, so this is the product rule that you have learned. And if your g at c is not 0, then you can simplify your f over g derivative at this point, okay, and this one is called the quotient rule, right, which is the bottom derivative of the top minus the top derivative of the bottom over your bottom square. Okay, and this one, it is a negative sign, so which one go first, it is pretty important. It is not the same as your product that you may have your first derivative of the second and the second derivative of the first. Okay, you can have this kind of thing as well for the product. Okay, let us do the proof, and then all the proof that we are going to show it to you. It is pretty important technique, okay, in terms of mathematics that we usually do. However, the technique that we talking about will be mainly on number 3 and number 4. Okay, so for example, because the f and the g are differentiable, then it means that the limit of this quotient, okay, over x minus c, and the limit of this quotient g of x, g of c over x minus c, they are exist. Okay, the limit exists. So let us do the calculation. For example, that this quotient for x is not c, then the thing that we need to find for the derivative of alpha f at c, it is this quotient, right? Okay, over x minus c. All right, and then actually it's the same as your alpha, and then f of x minus f of c over x minus c. Okay, and because this one is simply a constant, this one, the limit as your x goes to c exists, so it means that the limit, this one, as your x goes to c of the alpha, and then multiply by this quotient, okay, it is the same as your alpha, and then the limit of your quotient here, and this one, it is simply alpha and then a derivative of your f at the point c. Okay, And then what is this one? This one, it is actually your alpha f prime at c. Okay, so so this one can be found, okay, exist, okay, and it is equals to this value. All right, so this function alpha f is differentiable. For number 2, of course, they are the same, right? So for again, if your x is not c, okay, then your f plus g at x minus f plus g as c over x minus c, because this is the quotient that you need to calculate in order to determine your derivative of f plus g, right? So this one, it is the same as fx, and then gx. However, I mean, this one is actually f of x plus g of x, and this one as well, it is f of c plus g of c. But don't forget that we have this negative sign here. So let me just regroup your f together. So this one, it is your f of x minus f of c, okay, and then your g of x minus your g of c, and then actually it is over one fraction x minus c, right? However, in order to add the fraction, actually you can separate this addition, right, into two fractions, okay? The first one over x minus c, and then the second one also over x minus c. And then both of this quotient, the limit as your x goes to c exist. So it means that as you take the limit, okay, of this left hand side quotient, okay, over x minus c, this is the left hand side, your right hand side can be separated immediately, because each of the quotient, the limit as your x goes to c exists. So you can just do the separation as we have for the theorem of the limit, right? And then this one on your right hand side, the first one exists and it is equals to f prime at c. The second one also exists and it equals to g prime at c. But on your left hand side, it is actually f plus g prime at c. So it means that this function is differentiable, and the value, okay, is equals to this derivative of f and the derivative of g at this particular point, and then you add them up. Okay, so now as I told you that on number 3, it is some important technique that you should have learned. Okay, again, this one, it is for your x is not equals to c. If you look at your fg minus your fg at the point c over x minus c, again looking at this quotient, actually it is the same as your fx gx minus your fc gc, and then over this quotient x minus c. However, what we are going to do is to try to separate. For example, I mean, this addition, you can just immediately separate into like two terms like that, right? So we are going to try to separate into two terms as well. However, these two terms has no common factor, so we are going to create their common factor by subtracting your fc gx and then adding your fc gx. Okay, so on the top right now you got 4 terms. Okay, the original 2 terms are in blue, and the additional 2 terms are in red right here. Okay, at the bottom, they are on top. Okay, however, as we do the addition, then you should be able to see that you got one common factor among the first term and one common factor among the second term. Okay, so you can just grouping them together. So we got g of x and then f of x minus f of c okay, sorry, f of c over x minus c as one term. All right, and then the second term, you have your f as c, okay, and then you start from gx first minus g as c over x minus c as well, okay. And it is again that each quotient, okay, the limit as your x goes to c exists, okay. However, I mean, this one, of course, it is a constant, so the limit of a constant, it just that constant itself. The only problem that we may have is the limit of gx as your x goes to c. But we just prove that if your g is differentiable at the point, then don't forget that your g is also continuous immediately at the point x equals to c. So it means that the limit as your x goes to c of gx exists, and it equals to the function value gx, okay. So it means that as you take the limit of the quotient on your left, okay, the product, okay, of f and g minus the product of f and g as c over x minus c, it will be the same as the limit of your gx, the limit of this quotient fx and fc over x minus c, as well as the f of c, and the limit as your x goes to c of the last quotient about the g, okay. And this one, because it is continuous, is simply gc. This one is your f prime as c, because this limit of the quotient exists. This is simply f as c already. This one can be g prime as c, okay. So it means that on your left hand side, this one is the derivative of the product of f and g at c, and the product can be differentiable. I mean, it is differentiable, and the value equals to these two terms added together, okay. gc f prime at c and fc g prime at c, okay. You may think that, hey, I mean, why we are going to need this one, okay. As we told you that we need to set up a quotient like the one that we have in the derivative of f and g. So we need to try to, I mean, get some terms that have the common factor among the two given terms, okay, at the beginning. And you may say that, hey, why don't we try, I mean, can we try gcfx, I mean, and gc, I mean, one of them is minus and one of them is plus instead. Can we try it like that? Okay, so we'll let you try this kind of addition and subtraction by yourself as well. So let us go over the last property, okay, or the formula, which is the quotient rule. Okay, we are going to claim that your f and g derivative will be your bottom derivative of the top minus the top derivative of the bottom over your bottom square. Of course, your gc is not 0 first, okay. So for your x is not equals to c, we are again manipulate this quotient first, right, okay, as usual, okay. So to manipulate this quotient, actually it is the same as your fx over gx minus your fc over gc. Of course, you don't forget that your gc is not 0 over x minus c, and you do the cross multiply. So you got your f of x g of c minus your g of x f of c over gx, gc, and x minus c, right? Okay, again we are going to try to add some term, okay, so that your what is it on your top can be related to something that we have with the quotient that determine a derivative of f and g, okay. So you may try the same term, okay, as we did in the product. However, for this time, let me just add your FC, GC instead, and subtract your FC and GC as well. Okay, you may try the same term as your product first, and then you see what will happen, or what kind of problem will occur. Okay, now let us take a look. Okay, in order to create the term like the quotient of that determine the derivative of f, you need your f of x minus your f of c. So it means that you cannot combine these two terms directly, right? However, you may see that, hey, this one and that one, you got the minus sign here, so we can combine these two, okay. And immediately, because this one, you got your f of c and your f of c, and then you have the negative sign or the minus sign here, so you can combine these two together, okay. So let us do it like that. Okay, so the rate and the rate, you just pull out f a g of x, a g of c, all right, and then you have left by f of x minus f of c over x minus c, okay, this one of the quotient, and then subtract your f of c, right? And because you do the subtraction out, so now the subtraction is already out here, so you have your g of x minus g of c, okay. You need to have the minus sign because your negative is already here, over x minus c as well, and then all the quotient, you still have these two terms, right, at the bottom, gx and gc, okay, gx and gc. Again, don't forget that your g prime exists, okay. So it means immediately that your g is continuous, okay, is also continuous at c, and gc is not 0. So the limit of 1 over gx as your x goes to c can be 1 over gc, okay. So it will take care of this term. So immediately you can insert the limit to the left hand side here and the right hand side, okay. So your limit as your x goes to c of the left hand quotient will be equals to the limit as your x goes to c. I mean the gc can be out, and then this limit, because this limit exists, the fc can be out, and then this limit about the g, and then you can just do the over, your gc is out, and then the limit about your g of x, okay. So everything is all set because this one, your limit exists and it is your f prime. This one, the limit exists and it is your g prime. So you got gc f prime c minus fc g prime c over your gc square, because this one, the limit also exists and equals to gc. So it means that on your left hand side, it is the definition of your derivative of the quotient of f and g at the point C. Okay, so it means that the quotient, it is differentiable, and the value of the derivative equals to the bottom derivative of the top minus the top derivative of the bottom over your bottom square. Okay, so this kind of formula we are going to, sometimes, in this chapter we'll use it, okay, from time to time. However, this is just to, you know, make yourself feel pretty good that as we use all these formula in your math one, actually we can really prove it, or we can know how we got this formula like that. Okay, instead of, the derivative of f over g, it is a derivative of f over the derivative of g, which is all wrong. Okay, that kind of thing. So we are going to stop this video clip for the first one at this point. Okay, and then we are going to, of course, look at some more property. For example, you haven't go into the chain rule or that kind of thing, right? That it will make yourself pretty simple when you do, or when you need to find a derivative of a complicated function. Okay, so we'll see you next time. Bye bye.